Okay, welcome guys. We are going to start today another chapter, the chapter on deflections. Before, in the chapter of the beams and in the frames, we sketched the deflected shape, but we did not determine the magnitude of deflection. Now I'm going to teach you the virtual work method. This method is suitable to determine deflections in beams and in trusses and also in frames. Any kind of structure can be solved with the virtual work method. Now, in this method, let me first explain for you the concept, and then we're going to start today solving problems on deflection of trusses. Suppose that we are having a frame like this, subjected to a uniform load W in ton per meter, and a lateral concentrated load P. The deflected shape that is expected will be something like this. If we marked a point here N, this same point will move to this position N dash after deflection. We notice three things. We notice that point N moved in the X direction UX, and also moved in the vertical direction UY. So this is the vertical deflection, and this is the horizontal displacement or deflection at point N. Also, the tangent to the elastic line. Here, the central line is horizontal. Here, the central line is inclined with an angle theta at point N, which means that because this frame is in the 2D, any point in the frame after loading will undergo three displacements. Displacement in the vertical direction, and displacement in the horizontal direction, and rotation. The tangent to the elastic line after deformation is no longer horizontal, like in the undeformed shape, but rather it is subtending an angle theta n with the horizontal. Now, in the virtual work method, we will be able to determine one of these three displacements at a specific point at a time. Yani, you are not going to determine the magnitude of the deflections throughout the frame, but rather you will be able to determine either the deflection UX, UY, or theta at a specific point. If you want to determine the deflection at another point, then you are going to repeat the exercise or the equation of the virtual work method. Now, let me explain the concept here. This is called, or the original problem, this is called the main system. Suppose that I want to determine the value of Uy at point N. What am I going to do? I am going to take the same frame with the same geometry and the same supporting condition, like this. And this is point N. I am going to remove all of the loads, and I am going to put a unit load at point N in the deflection, in the direction of the desired deflection. It is required to determine the vertical deflection. This means that I'm going to put a vertical unit load, whether it is going down or it is going up according to the expected deflection. Now, it is expected, due to the presence of this distributed load, that the frame will deflect downward. When I'm going to assume the unit load, I'm going to take the unit load in the vertical direction and pointing downward. Why? Because I want to get the vertical deflection, so I'm going to put a unit load and I'm going to remove all of the loads, and I'm going to assume that the deflection here is downward. Then the unit load will be in the same direction of the predicted or expected deflection at point N. What is the concept of the virtual work method? Let us distinguish first between the original frame or the real frame with the real applied loads and this hypothetical system that we selected. This one is called the unit load system. Okay. Now, if you cut a section here at any arbitrary point and you cut a section here at the same point, okay? I selected an arbitrary section and we cut here through that section. Now, when you take this part of the frame, what are you going to have? I'm going to have 3 internal forces. Because this is a frame, then I'm going to have 3 internal forces, N1, Q1, and M1. Okay? And at this point here, now we will notice that there is a vertical deflection, delta, and we are having here rotation, theta, and we are having some sort of shear deformation as well. Okay, let me explain for you the concept of the virtual work method. The virtual work method says that the external work done due to unit load and deflections of main system is equal to the internal work due to internal forces of unit load system and deflections of the main system. Okay, this is the concept of the virtual work method. We don't understand. Okay, let me explain that. The external work done due to the unit load and the deformations of the main system. What is the definition of the external work? It is the force multiplied by the distance. So the left-hand side of this equation is saying that you should take the forces from this system and multiply by the displacement of the corresponding displacement of the main system. One student will tell me, but this cannot happen because this is a system where I removed all of the forces and I am only applying the unit load. And this is the original system where I am putting all of the loads on the frame. Well, it is the virtual work method. It is something hypothetical. So the scientist who put this rule, he said that I will take the unit load here from there and I'm going to multiply it by the corresponding displacement. This is an external virtual work because it will not happen, but he assumed that. Type, what is the corresponding displacement at point N? Point N is having 3 displacements, ux and uy and theta. But the load is in the direction of uy. So this means that the work done by the load will be 1 multiplied by uy. So the left-hand side here will be 1 multiplied by uy equals to. the internal work due to the internal forces in the unit load system and the deflections of the main system. What does this mean? It means that at this arbitrary section, we found that we are having three internal forces. We are having N1 and M1 and Q1. What is the corresponding deflections in the main system? Here, this point, it was there, and then it moved in this direction, for example. So it moved in the axial direction by a distance delta. And also, for the bending moment, we are having an external moment, and there is a corresponding angle of rotation theta. And also there is a shear force. Corresponding to the shear force, there will be a shear displacement. Let me clarify here the shear displacement. It is not clear in this figure. If you are having an element like this, and it is subjected to shear force, what will happen? Now this will deform like that. Okay? So the amount of displacement here multiplied by the shear force will give us the work done due to the shear force. Type. Let us again go back to the statement. It says that internal work done due to the internal forces of the unit load system. If I will take N1 and I will multiply this by delta, because this is the displacement in the main system corresponding to N1. And for the moment, the rotation is theta, so I'm going to multiply the moment by theta to get the internal work due to the moment. And I will take the shear and I will see how much shear deformation I have in this section, which is this amount here, and I will multiply the displacement or the shear deformation multiplied by the shear force. But take care. Why not you take this section here and section here and section here? Well, it says here the internal work by the internal forces, all of the forces. Then you will have to determine the internal work caused by the shear and the normal and the bending at this section, and add to it the internal work in this section and in this section, in this section, in this section, in this section, throughout the frame, which means integration. Therefore, I will say here, this is integral N1 multiplied by delta dl. We are integrating along the length of the frame. So here, you are multiplying the internal force from the unit load system, and you are multiplying delta, which is the axial deformation at this section from the main system. And you are integrating through the length, because the normal force is changing throughout, and the axial deformation is also changing throughout. The same thing for the moment, or the same thing for the shear. I will take Q, let us say that this displacement, for example, is epsilon, multiplied by epsilon dl, plus integral the moment N1 theta multiplied by dl. So you notice here, each internal force is multiplied by its corresponding displacement. But because the normal force N1 is changing throughout the frame, and the shear force is changing throughout, and the bending moment is changing throughout, and also the displacements are changed throughout, therefore I will have to integrate. So I'm adding the internal forces or the internal work done due to the normal force plus that caused by the shear plus that caused by the bending moment. This is the translation of the virtual work concept. Let's read that again. The external work done due to the unit load and the deflections of the main system. I am taking the unit load from here and I am multiplying by the corresponding displacement. There is nothing else except this unit load. Of course, because the reactions will be multiplied by 0 because these points are not moving. So the only point where I am having a force corresponding to a displacement is point N. Okay, this is the left hand side. Now the right hand side, if you take any arbitrary section in the unit load system and in the main system, you will have N1, Q1 and M1, and you will have delta, theta and epsilon. When you multiply N1 by delta, you are getting the internal force due to the normal force. But you need to integrate that. Okay? And when you multiply Q by epsilon, you are getting the internal work done due to the shear. But you have to integrate throughout the length. And also for the moment, you have to multiply this by theta in order to get the work done by the moment. Very good. Before we go into another part here, let us examine here. Now we understood why I selected this load to be a unit load. Because anything multiplied by unity is that thing. Therefore, I will be able to determine Uy immediately. If you put here 2 tons, you multiply 2 multiplied by Uy, then you will have to divide this by 2. That is the reason that we selected this to be a unit load, so that we can straightforward get the value of Uy that we want to get. Another thing that we learn from here, that the displacements in the frame, now this displacement here at any point is actually caused by 3 components. It's caused by the normal force, and it's caused by the shear, and it's caused by the bending moment. All of them will contribute to the magnitude of Uy. When you go into the numbers, you will discover that the majority of this deflection, Uy, is coming from the component of the bending moment. So basically in the frames, for example, we can neglect the shear and the normal force, and we can live with the bending moment. Similar to the beams, we can live with the bending moment because the deflection caused by the moment alone maybe constitutes 99% of the magnitude of the deflection Uy. But one student will ask me, how about trusses? In the trusses, I don't have shear and I don't have bending moment. But in the trusses, I will only have the deflection is caused or is mainly caused by, or is only caused by the normal force. Okay? Whenever we are studying frames or beams, I'm going to take the bending moment component. When we are studying trusses, I'm going to take the normal force component. If the 3 components are significant, then you have the right to take all of them. Now, still we don't know how we can calculate delta and epsilon and theta. Still this equation is not clear. Now let us clarify this. Take care. Now, integral N1 delta dl, this is equal to, from simple structural mechanics, we can prove that this is equal to integral N1 N naught dl over EA. This component here is the magnitude of the deflection caused by the main system. Or this is the deflection corresponding to, or the axial deformation in the main system. So we are having N1 is the internal normal force in the unit load system. And we are having N naught is the internal normal force in the main system. Similar, if you want to get the deflection Q1 epsilon dl, this is integral Q1 Q naught dl over G A, and integral M1 theta dl, this is integral M1 M naught dl over EI. So here we are having, this is the deformation caused by the normal force, and these are the deformations caused by the shear, and these are the deformations caused by the bending moment. Take care. What is E? It is the Young's modulus of the material, which is the slope or the slope of the tangent to the initial portion of the stress strain curve. What is A? It is the cross-sectional area of the beam. Okay? For example, if the element here is having the same cross-sectional area, then this means that this will be the value of A. If the value of A is changing, it will be considered as a term inside the integral. It will be changing with the length of the frame itself. And also G is the shear modulus. The shear modulus G is equal to E over 2 into 1 plus mu, where E is the Young's modulus and mu is the Poisson's ratio, okay, which is the ratio of the transverse strains to the longitudinal strains. I'm sure that you studied this in structural mechanics, okay? And here is the cross-sectional area. And for the moment, this is the Young's modulus E, and this is the moment of inertia. You remember in 212, you took chapter 9, where you calculated the moments of inertia of the section. So I here is the moment of inertia of the section, okay? Finally, we can write down the equation, the virtual work method. We can write here that 1 multiplied by uy is equal to integral n1 n naught dl over EA plus integral q1 q naught dl over GA plus integral m1 m naught dl over EI. What is known and what is unknown in this equation? Okay, now I am having the main system. For this main system, I will have to determine the normal force diagram, the shear force diagram, and the bending moment diagram. I will have to solve for this main system the 3 internal forces. I will get the normal force, the shear force, and the bending moment. And then, if I need to determine the vertical deflection at point N, I will take the same geometry, remove all of the forces, and put a unit load in the direction of the desired deflection and at the point where we need to calculate the deflection. Now, this is the main system. From there, I will have to draw the normal force N1, the shear force, and the bending moment. And here I will have to draw the normal force, shear force, and bending moment. Then we have to integrate the product of N naught and N1 along the length, the Q naught and Q1 along the length, and the moment M naught and M1 along the length. This is for the most complicated problem. But if we are talking trusses, يبقى 4 trusses we don't have moment, we don't have shear. 1 multiplied by uy will be equal to integral n1 n naught dl over ea. But take care. Now, why did we integrate here? Because the normal force is susceptible to change in the frame along the member. You might have a normal force here, or a force that is applied, a concentrated force applied here, so the normal force is not the same. Okay? Therefore, we need to apply this in the form of integration. But let me ask you a question. In any truss member, according to what we solved together in chapter 2, in the same truss member, the normal force is constant. Therefore, I can take N1 and N naught and EA outside the integration. And all what I will have is the length integral dl is equal to L. Therefore, in the trusses, this equation is changed into y multiplied by uy is equal to sigma n1 n naught L over EA. And why is sigma? Because I will have to determine this product for each and every member in the truss. How many truss members do we have? 26. I will calculate the product N1 N naught L over EA in each member, and I will add all of them together to determine the magnitude of the deflection at the point required. Of course, this cannot be true or cannot be easy to understand except if we applied a problem. So I'm going to solve with you 2 problems in the deflection of trusses. Before we start the problem, now the final equation that we have reached whenever you are getting the deflection of trusses is this equation. Okay? The deflection at any point, whether horizontal or vertical, will be the summation of N1 N naught L over EA. Example. Find vertical deflection at point C. Consider EA is constant. Now we are having a truss like this. This point is hinged support, and this is a roller support. We are having, this is 5 tons, and we are having a load here 2 tons. This point A, B, C, D, and E. These distances are given to us, and this is 4 meters, 4 meters, and this is 6 meters. We need to calculate the deflection at point C. Now, take care that due to the application of this force, we can have the system deflected like this. Okay? So we are having here a vertical deflection Uy that we want to get. Okay? So what are we going to do? We are going to say that according to the virtual work concept, we can say that Uy at point C is equal to sigma N1 N naught L over EA. If each member is having a different Young's modulus and a different area, then I cannot take EA as a common factor. It will have to be considered in each member. But he told me in the question you can consider all of the members are having the same cross-section and are having the same Young's modulus. They are all composed of the same material and of the same cross-sectional area. Therefore, we need to determine the normal force and the shear and the normal force due to the unit load and the shear and the normal force due to the main system. Let us solve first for the main system. Now, in the main system, we are going to solve this truss. So we are having a vertical reaction here. From sigma Fy is equal to 0, this will be 7 ton. You can take moments about this point to determine this reaction. You are going to have 2 multiplied by 8 and 5 multiplied by 4 is equal to the reaction multiplied by its distance, which is 6. From there we get this 6 tons. From sigma Fx is equal to 0, there should be a reaction in this direction 6 ton. Type. We need to determine the normal force N naught in all of the members of the truss. If you want to determine all of the forces, we will have to work with the method of joints. Okay? We can start either at point C or at point E. Why? Because at point C we are only having 2 unknowns, and at point E we are also having 2 unknowns. So imagine that we started from this point, we are having a vertical load of 2 ton. I will take the equilibrium of forces at point C, sigma Fy is equal to 0. This force will be tension 3.33. And from sigma Fx is equal to 0, this force will be compression, and it will be negative 2.67. Now, I cannot go to point D, because at point D I am having 1 unknown, 2, 3, and I'm only having 2 equilibrium equations. So I can go to point B. From sigma Fy is equal to 0, this force will be 5 tons. From sigma Fx, this force will be negative 2.67. Okay? Then we can take the equilibrium of point D, we can solve for this force and this force, and we can obtain this force to be 7.5, and this force here will be negative 2.81. And then we can take either equilibrium of forces at point A. We know the force here is 2.67, the force is 2.81, and we are having the 2 reactions. We can determine from sigma Fy the force in this member. If you did this, this force will be compression, and it will be negative 4.5. Now you completed 1/3 of the question, because we know from the virtual work I need to determine N naught, which is the internal forces in all of the truss member due to the applied load case. Okay? Now we are going to go to the unit load, we are going to take the same truss exactly, now where you want to get the reaction, where you want to get the deflection, I want to get the deflection at point C, and this is the vertical deflection, right? يبقى I'm going to remove all of the forces and only I will put a unit load here. In which direction I will put the unit load? It is expected in the main system, because of the 2-ton force here and the 5-ton force, the truss will go down. يبقى therefore I will assume the unit load in the expected direction. What if I was mistaken and I assume the unit load upward? Then the deflection you are going to get, when you get Uy, you are going to get Uy negative sign. It means that the deflection should be opposite to the direction of the unit load assumed. But it is very obvious here that this is a cantilever-like truss, then it will go down due to the effect of the vertical loads, then point C will go down. That's why we assume the force like that. What else are we going to apply? Nothing. Now you remove all of the forces and you just put the unit load in the direction of the desired deflection at the required point, which is point C. Now you need to solve the problem. Again, this is another problem where you need to determine N1. Again, I'm going to use the method of joints. So I will start by the reactions. Here I'm having 1 ton, and here I will have a reaction. By taking moments about this point, we can prove that this reaction is 1.33, and this is 1.33. Similar to what we did here, I will start by solving at point C. I will take the equilibrium of forces at this joint. From sigma Fy is equal to 0, I will get the force here to be 1.67, okay? And the force here will be compression from sigma Fx is equal to 0, and it is negative 1.33. From the equilibrium of this joint, of course, this will be a zero member because I'm having 3 intersected members. 2 members are collinear, and the third one is not collinear with them, and the point or the joint is not loaded. يبقى this should be a zero member. Also, this should be a zero member. If this is a zero member, you can cancel it out. Again, you are having 2 members that are collinear, and the third is not collinear with them, and this joint is not loaded. يبقى this is also a zero member. Okay? From the summation or the equilibrium of forces in the horizontal direction, this also should be compression, negative 1.33, and this also should be tension, positive 1.67. You can take after that the equilibrium of forces of joint at this joint. Here the reaction will be in equilibrium with this force, therefore this one should be negative 1 ton. Okay? These forces are the N1 forces. Now I will organize my answer. I need to multiply the 3.33 by the corresponding force by the corresponding length divided by the corresponding area. But he told me that the area is constant, so I can divide by the area at the end. I will come here and I will put my answer in a tabular form. But take care. There are some members that are zero members. We don't need to write this one because 0 multiplied by 5 will give 0. And 0 multiplied by 2.85 will give 0. I don't need to include these 2 members in my table. I will make a table here like that. This is the member, and this is N node, this is N1, and this is L. Okay, we are having here member AB, and then BC, and then CD, DE, and AE. The other member, which is BD, I'm not going to include it here because I'm having 0 multiplied by 5, it will give nothing. And the member AD also I'm not going to write it because 0 multiplied by 2.81 will give nothing. Here I'm having, let us write the forces with their sign. This is negative 2.67, negative 2.67, and then positive 3.33, and positive 7.5, positive 7.5, this is negative 4.5. Okay, and for the forces here we are having negative 1.33, negative 1.33, positive 1.67, 1.67, and negative 1. We can determine from the geometry, this is 4 and this is 3, therefore this is 5. So I'm having the length here is 4 meters, the length of member AB, and also for member BC it is 4, and for member CD it is 5, and then 5, and then 6. Then you are going to get the product N1, N naught multiplied by L. You are going to get the product of this number and this number and this number, maintaining the sign. Negative and negative will give positive, and negative will give positive, and so on. And then you need to add these numbers together. And if we did this, you will find that it is 148 and 45.8. Now this means that the deflection UY at point C is sigma N naught N1 L over EA, and this term is obtained to be 145.8 over EA. Of course, he told us in the question that EA is constant, so it will have to be taken like this. If the value of EA is not constant, for every member, you are going to put in a separate column the magnitude of EA, and then divide the product N1 N naught L divided by EA, and then get the summation. But here we are having EA is the same, so we can take EA as a common factor. Take care. Because you got this positive, you notice that the negative force is corresponding to a negative force here, and the positive force is corresponding to a positive force, so they are all adding up. You are not getting a negative deflection, but you are getting a positive deflection. What does this mean? It means that the deflection at point C is in the same direction of the unit load. Now, going back to chapter 2 and 3, where we sketched the deflected shape like that, we were just sketching, but we did not know the magnitude of the deflection itself. Now in this chapter, you were able to determine the amount of deflection. Why is it important to calculate the deflection of any structure? To let you informed that the design of any structure is not only to satisfy the internal force that will develop in it, but also you will have to satisfy the amount of deflection. This amount of deflection is measured according to the permissible value for each country, according to the use of the structure, and according to the finishes that you have. Imagine that this truss is supporting glass or is supporting curtain wall. The curtain wall is so sensitive to deflections, then the amount of deflection should be limited. What if it is not limited? Then you will have to change the cross section of the members. You can increase the area. You can use a material with larger Young's modulus. Of course, for the loads and for the internal forces, you cannot help it. They are always there. But you have to, in order to reduce the deflection, either that you change the system itself, you provide a support, or that you increase the cross-sectional area or the Young's modulus so that you are able to reduce the amount of deflection and make your structure applicable. Okay? Now, let us solve another question. Another example. It is required to determine Uy at point C. By coincidence, it is having the same letter. Now I'm having a truss like this. And we are having here loads like that. This is point A, B, C, D, E, and F. The geometry here is given to us. This is 2 meters, and here the height. This is 1 meter and 1 meter. It is required to determine the vertical deflection at point C. Again, we need to calculate N naught. We need to determine the internal forces due to the main system. This is a symmetric truss subjected to symmetric loading. يبقى we don't need to solve all of the question. We can solve only half of the question. Now the total sum of the forces that we have is 20 tons. So here I will have 10, and here I will have 10 tons. Okay? We can start by equilibrium of forces at point A, and you can take sigma Fy is equal to 0. So if you did this, you will have a positive force here of positive 20, and you can solve for the force here by taking equilibrium of forces at point A. You can determine the force in the member AB from sigma Fy is equal to 0. So here you are going to have compression, and it is negative 22.36. Now you are having a joint where you are having 2 unknown forces. So I can determine the force in member BD and BC by solving 2 equations in 2 unknowns. You can get this one. It will be negative 16.8, and here it is negative 5.6. Now you can take either joint D, you can take joint D and solve for the forces here. Of course, this member will be also compression and it will be 16.8. So I will have this member will be tension and it is plus 5 ton. Now I don't need to determine the force in this member because it is the same as BD, and the force in member EF it will be the same as AB, and the force in this member it will be the same as BC, and the force in member CF will be the same as AC because the structure is symmetric. Okay, so when we notice that we are having a symmetric truss, you don't need to solve for all of the forces that you have. طيب. For the unit load case, again, we are removing all of the forces that we have, right? And we are putting instead a unit load in the direction of the desired deflection. He wants to get the vertical deflection at point C. It is expected that point C will go down because it is loaded this way, okay? Therefore, we need to determine the forces N1. We have to solve here by the method of joints. Again, the structure is symmetric and the loads are symmetric. Here I'm going to have 0.5 and a reaction 0.5. This is a zero member and this is a zero member because we are having three members intersected, two members collinear and the third is not collinear with them, and the joint is not loaded. This is a zero member. Now when you take the equilibrium of forces at this joint, you will get the force here is plus 1 and the force here is compression and it is negative 1.2 and here it is negative 1.2, and from the equilibrium of forces, of course, this member will be also having compression and it is negative 1.2. So from sigma Fy is equal to 0. This force in this member here will be 1 ton. Let us organize our answer in a tabular form. This is the member designation, N naught, N1, and the length, and then the product N1, N naught multiplied by L. We are having member AC, and then member AB, member BD, and member DC, okay? Take care. Member BC will be multiplied by 0, so I don't need to include it here. Member AC is repeated twice because this is symmetric. I will have to multiply this by 2. And also member AB is multiplied by 2. Member BD is multiplied by 2. The only member that is repeated once is member DC because this is exactly on the line of symmetry. So this will be multiplied by 1. So instead of writing all of the members of the truss, we just included half of them. And of course, if any member is not repeated, it will have to be included in the table. Also, if I'm having a zero member, I don't need to write it in the table because anyway, the 0 will be multiplied by this force and the result will be equal to 0. If you put this in a tabular form, you are having AC is 20 and this is negative 22.36, negative 16.8 and plus 5. Okay? So we are having here, this is plus 1, the corresponding force, and this is negative 1.2, and this is negative 1.2, and this is plus 1. For the length of the member AC, it is 4 meters. For the member BD, if you calculated its value, of course we can get this from the geometry. We are having the length here is 1 meter, and this is 2 meters, so the hypotenuse will be root 2 square plus 1 square, which is root 5. So this is 2.236. And also for the other member, 2.236. And for member DC is 2 meters. Then you get the product of each part. Okay, you multiply here. And don't forget that you will have to multiply this by 2, multiply this by 2, multiply this by 2, multiply this by 1. And you get the summation in the end. And it will be 356.65. This is 365.6. This is the summation. The summation of all of these forces. Therefore, Uy will be equal to sigma N1 N naught EA L multiplied by EA. And if you did this, you calculated this term, which is sigma N1 N naught L, which is 365.64 divided by EA. Now again, in this problem, I'm assuming that all of the members are having the same cross-section and composed of the same material with the same Young's modulus. That's why we wrote the answer in terms of EA. If he gave you in the question the magnitude of EA and it is different for each member, you will have to include here in the table the magnitude of EA, and you will have to divide this product by the magnitude of EA. Otherwise, if it is constant, you can take it outside the summation as we did here, and the final answer can be in terms of EA, as you can see. What do you understand from the positive sign? Because the deflection is positive, it means that it is in the same direction of the unit load. If this truss is deflected, it will deflect something like that. Like this. We got the magnitude of the vertical deflection at point C. Okay? Now you can start solving the first group of assignments in assignment number 7 on the deflections, and this will be on trusses. You will have to solve all of the forces in the truss using the method of joints, because you need all of the forces, so it is better to use the method of joints. And then you remove all of the forces and put the unit load in the direction of the required deflection. Solve for the forces, so you are getting N1 forces. So this is 1/3 of the question, this is the other third, and then you put your answer in a tabular form. You add up the product of N1 N naught L, and if the value of EA is constant, you can take it outside, and you can get the summation of N1 N naught L, and then divide by the common factor EA for all of the members. Okay? I hope this is clear. Thank you very much.